Hello and welcome back. So today we continue with our learning of mechanics. So mechanics is what we're going to be studying the entire first semester. So all summer we're studying mechanics or motion. And mechanics is broken down into two parts. The first part is kinematics. So that's what we just finished. We chapters 1 through 4, we learned all the foundational information of kinematics, like setting your or picking your coordinate system, marking your position, changing position, velocity, acceleration. So, all the fundamentals of motion, the fundamental characteristics of motion, is what we studied in the first 4 chapters. And then this chapter now, we began our studies of dynamics. So, kinematics being the characteristics, dynamics is the why. It's why motion happens. And we'll learn that motion happens all because of a force that gets applied. And that's literally it. So you apply a force to something and it starts moving. So we're going to study why that happens, why these forces cause motion. And we're going to study a variety of different forces too. Chapters 5 and 6 are all about forces and Newton's laws of motion, particularly, that codified what a force is and proves that a force is really what causes that motion. And our picture right here, our cover picture, is actually a problem that we'll solve in this lecture too. And I do want to draw your attention to this part of the picture right here. So it might look a little funny. We had in the last chapter, chapter 3, when we were drawing our right triangle, that hypotenuse, it could be A, could be V, it could be D. And whatever the hypotenuse is, that's what the components were. So if the hypotenuse was the acceleration vector, then the components were a sub x and a sub y. Same thing with velocity and displacement. So in the picture here, it looks like we have two things going on up here. We have our vector right here. So we have our vector pointing out in one dimension. It's just acceleration. But the 255s and the 57 Newton, they're not labeled. And really what they are is they're forces as well. This one in particular is the force of friction. And then these forces here are applied forces. So it's the force that this gentleman is putting on the cord, and the same thing up here. This gentleman is applying a force, both of them are applying a force of 55 newtons to the sled. And we see that the direction of the force is the same as the direction of the acceleration. But we don't want to think that this acceleration is the base of a triangle. That's not the case. That's not the case at all. It's just a poorly drawn picture. And, well, I shouldn't even say that. The purpose of the picture is to show that the direction of the acceleration is in the direction of motion, or in the direction of the applied force. So even though you're applying the force this way and this way, the resultant force goes this way, and it's in the same direction as the acceleration. So you have a triangle here and a triangle here, and the vector A is actually one-dimensional motion. The sled is moving in one dimension, and it's the force that's creating the right triangle. So even though our acceleration is a vector, in this picture here, it's just moving along the snow. So here it's one dimension, and then the force is what's 2 dimensions, and so you have your angle and your hypotenuse there. So we'll go through that again when we get to this problem to solve. So here's our outline, and we'll learn force and mass, and we'll learn a key distinction too. Mass and weight are two different things. Mass is a scalar and weight is a vector. But we'll get into that too with all our definitions. And then here's our 3 laws. And then we'll also see the vector nature of forces. So force and mass, what is it? Or what are they? So the force a force is a push or a pull, and that's it. It's just going to be a push or a pull that acts upon an object as a result of its interaction with another object. And so forces result from interactions. So a little bit more on this interaction. It's a push or a pull. So we can think of that in very broad terms. So think of a baseball player throwing a baseball. So that throw is a push. It's pushing the baseball. Oftentimes we think of pushing each other or shoving each other or pushing a shopping cart. But in reality, there's a lot of actions that are pushes, and throwing a ball is one of them. If you throw a football, same thing. If you kick a football or you kick a soccer ball, that's still a push. It's still, you're pushing it away. You're pushing the object away from you. And then a pull would be like if you picked up a bowling ball and you pick it up off of the return, and you're going to pick it up off the side, and then you're going to put your fingers in it. So when you pick up that bowling ball, you're pulling it towards you. Even when the sled that's on the front cover here, that's a pull. The guys are pulling the ropes. So there's a pull there. And then pushing is when you're making something move away from you. So you don't often think of a push as a throw, but it is. You're pushing the ball away from you. And then the interaction, it's your hand. If you're the baseball player, it's your hand and the baseball that are interacting. So your hand is one object and the baseball is the other object. So the interaction between the two, your hand is going to push the ball. So the force results from that interaction. Same thing with your foot. If you're kicking a football or kicking a soccer ball, your foot is an object and the ball is an object. And your foot is exerting that force on the ball to push it away from you. We can also think of environmental or the environment as part of the interaction too, or the environment and its effects. So wind making a leaf move is an interaction. It's an environmental interaction or a force interaction between two objects. It's the wind and the leaf. So the wind is blowing and it encounters or interacts with the leaf, and the leaf is hanging on a tree. So it's the wind is not going to carry up in this scenario. It's not going to take the leaf and carry it away. Rather, it's going to make the leaf move on the tree. It's going to just blow in the wind, but it's going to stay connected to the tree. So that's where we get the concept of air resistance. In the last chapters, we said to ignore air resistance and or say that it was negligible. So that air resistance is basically a form of friction when the air is interacting or when the wind is interacting with the leaf. So the leaf is going to move in the wind, but it's still going to stay attached to the tree. But if the force was really strong, it could take the leaf off the tree and carry it away with it. But either way, that's an interaction, and it's a force. The wind is exerting a force on the leaf. Another example, too, that we often don't think of as a force relationship is the example here. So you're holding an object. So think of the baseball player holding the baseball. Your hand is holding the baseball. So you're holding that object, and your hand is exerting that upward force. Even if you're just standing there and you're holding it. So if you're standing still, and so you're standing still, and in your hand is the ball, and you're just holding it. So you don't think you're exerting a force on it. It doesn't feel like it because it's not strenuous. And you're holding this ball in your hand. You're just standing there holding it. But you are exerting a force on it. You're exerting an upward force that counteracts or counters the downward pull of gravity. So remember when you drop the ball and it just takes that parabolic path? So that parabolic path downward, that's gravity acting on it. So if you drop the ball or you throw the ball, gravity, or that picture that we had where you threw the ball towards picture A or point A, but the ball curved down to B and you found that distance there. So gravity's what pulled it down. So gravity's trying to pull it out of your hand here. So you're exerting a force to keep the ball from falling or to keep gravity from pulling it down. So gravity's a pulling force, and yours is you're pulling it up because force pairs are always in combination. So when gravity's pulling, gravity's pulling downward, you're pulling upward. So again, it doesn't sound like it sounds like you would think it's that you're pushing it upward. But force pairs are always push push or pull pull. So if gravity's pulling downward, you're pulling up against gravity to keep that ball from falling. So your hand's pulling up, and then the wind is pushing the leaf, and the leaf is resisting by pushing back. And if the force overcomes that resistance, it'll rip the leaf off the tree and carry it away with it. So either way, again, we have force pairs are always a push-push combination or a pull-pull combination. So force and mass, force is a vector, and all vectors have a magnitude and a direction. So the magnitude is the strength. So in this case, when we're talking about a force, it's the strength of the force. How strong is that push or how strong is that pull? So when we talked about velocity, we talked about the magnitude of velocity is the speed. So it's a measure of how fast the speed is or how fast the acceleration is. Here, when we're talking about force, it's a strength. So we'll see the strength of the pull, or the strength of the pull here, or the strength of the tension. We'll see also the strength of the resistance. So friction is a force that is in the opposite direction of motion. So we'll see how strong the friction is too. So pretty much all the vectors we're going to be talking about now that are force vectors, friction, tension, contact forces, we'll get into those, but all of those are going to have a magnitude that's really telling us how strong that vector is. And then, of course, since it's a vector, it has a direction too, and the direction is the direction of the push or the pull. So the magnitude corresponds to how strong or how hard the person's pulling the sled in this picture, and the direction corresponds to the force that's causing the motion. So the person pulling the sled is the frame of reference, and then the motion is going to be in that frame of reference and in the direction of the force. So here's the motion, and there's the direction of the force. So if you put if you sat a child right here or a person on the sled, the weight of the person is pushing downward, pushing down the sled, and that's a force vector. Weight is a force, and we would be showing here, that weight or that vector, we'd write that in the downward direction. We'd have that weight down here. We would show that, but we're going to cover that too in our free body diagrams. So some vector properties, again, just a little refresh. Vectors have a magnitude and a direction, so they're broken down into their components. So we see the same thing here. We see our force vector, and then we see the components, f of x and f of y. And our frame of reference, or our free body diagram, is right here. That's what we want to look at. We want to look at that in the same way that we looked at the vectors in chapter 3. So we're going to take that chord, and we're just going to isolate the chord and draw our forces on that. And then from there we can calculate everything, or calculate the desired parameters just by looking at, or just by using our trigonometry. So we have our component vectors, f of x and f of y, and then the trigonometric relationship. But then that's also, when we look at this relationship here, that's the resultant force. It's called a resultant force because if you pulled in the x direction and pulled in the y direction simultaneously, you're going to see that force go that way. And we'll see in a little bit that the acceleration too, that we looked at in the last slide, but we'll get more into acceleration when we look at Newton's laws. So just a summary there again, that resultant force goes in this direction here because you're pulling in this direction and this direction. So even though x and y are independent of each other, the resultant force is dependent on both. The resultant force is very much dependent on the x and y directions of the force. Similarly, when you put an incline in place, you're going to have this person pulling up here along the resultant, and it's going to give you an x component. But note that he's just pulling straight up the incline, so he's not lifting it. So the f sub y right here is 0. And that is in line with our equation, our vector equation, that says the force is the sum of the x and y components. And this, in this particular case, the y component is 0. So the force is equal to the force in the x direction. So different types of forces. It's always a push. Forces are always a push or a pull. And you can have a single force, just one force, and that's what we show right here. This is what we show right here. So this is one force, and it's tension. This is one force as well, it's weight. Here's the normal, that's one force, and this is one force. But in this picture right here, we have two forces. We have our normal force, typically, we write that as a capital N. That's our vector, and then right here, the little n is in the y direction. That's the component, actually. And then the friction force right there, that's the only force that gets written in lowercase. And it's also the only force that will never have a y component. Friction's always against the motion. So if you're pulling something or pushing something in the x direction, friction is going to be in the negative x direction. It's going to oppose the motion. I said it never has a y component, but actually if you reverse something, if you had a wall, say you had a wall and you're pushing something up the wall, in that case then friction would be in the y direction, and friction in the x direction would be 0. So friction, the key that you want to remember here is that friction is a one-dimensional force. It only acts in one dimension. So if you're moving something in the x direction, the friction force will be in the x direction as well. And if you're, but it'll be the opposite. So if you're moving something in the positive y direction, friction will be in the negative. If you're moving something in the positive x direction, friction will be in the negative x direction. If you're moving something in the positive y, friction will be in the negative y. So friction again is one-dimensional, and it goes against the motion. But back to our net topic right here. So we looked at all the other pictures are a single force, just one force acting on the object. But this friction force shows two forces. So the friction force here, we have our friction force and our normal force. So the total force is equal to the friction force plus the normal force. So this is our net. That's our net force. And it's a summation. The net force is always a summation of all the forces, summation of all the forces involved. But then here you have your single force again. So the normal force by definition is that it's always going to be perpendicular to the surface on which the object is resting. So here we have a box resting on a level surface. So the normal is here, and you can draw it from the center of the object, or more realistically, you could put it here, because that way it indicates that the normal force is a support force. It's always going to be holding up or bracketing the object. So it's actually the normal force is always perpendicular to the surface that the object is resting on. So and the object's resting on a surface, and it's being supported by this force. And so when we think of a table and your books on a table, all the objects, your computer is on a table, so we don't physically see a force in that case here. We don't actually see a rope that's being pulled. We don't see boxes that are in contact with each other. We know that friction is available, but we don't really see it in that case. We don't see the weight. We see the mass of the object, but the weight is something different. But in terms of the normal force, we know we got all these objects on our desk, and we know that we're sitting in a chair. So that chair is supporting us, and the desk is supporting all of our objects. But we don't see the force, and that's because the chairs and the desks, they're manufactured to support a certain load. So chairs are typically designed to support people of 400 pounds, typically in that range or perhaps a little more. So any person could sit in that chair and be rest assured that the chair is not going to collapse underneath them. And the same thing with your desk. All the stuff that you put on your desk, it's built to withstand a maximum load. Probably a few hundred pounds for your desk as well. And that ensures that the desk is not going to, again, collapse out from underneath all the objects you put on it. So the normal force is built in to the chair and the desk. And by nature of its building, it's going to always be perpendicular. It's always going to hold up. It's going to hold up everything. It's going to make sure that the chair doesn't collapse. It's going to make sure the desk doesn't collapse. So the normal force, again, is a support force. It's a structural type of a force that makes sure that the surface doesn't collapse under the weight of the object that's on top of it. So that's our normal force. Contact is typically when we have boxes in contact with one another, and we're going to solve a problem with that. Friction is, again, we show that we talked about that one. And then tension, here's our tension. It's when you make a cord or a string or something really taut, you get tension in it. And then and that's always going to be a pulling force. Tension's always going to pull, and it's always going to be exerted on an object by some kind of a rope or a cord or a string. And then that brings us to weight. So weight is a vector W, and it's the pull of gravity on an object. So the pull of it's basically, if we think of the Earth, the center of the Earth, gravity is always being, the Earth is pulling everything to the core. So a gravity is going to be pulling that object or pulling on that object, trying to pull it towards the center of the Earth. So an object can have several forces acting on it at any given time. So that's always going to be a net force. And then similarly, a book on a table experiences a downward force due to gravity, as well as the upward force due to the table. So if we have our table here in our book, we have the downward force due to gravity, that's the weight, and the upward force due to the table, that's your normal. So we have the normal force and weight acting on this book. But then if you push the book, if you push this book, that's an applied force, and that's going to be applied by your hand. You're going to push the book. And then because it's sitting on that surface, it's going to have a friction force too. So there's four forces. We have friction, we have an applied force, we have the normal, and we have weight. So they're the four forces applied to that book. And that total force, again, is the vector sum of the individual forces acting on it. A very important concept with force is that it's the first key component of Newton's laws. So all of Newton's laws are talking about force, and then what happens as a result of that force being applied. So the total force or force is the first key component of Newton's laws, and then mass is the other. So mass is your object. So here's force and mass. Mass is a measure of how hard it is to change an object's velocity. So if you throw something and you put it in motion, say you throw a bowling ball or you're throwing it down the alley, and somebody wants to stop it. Somebody wants to stop the ball from moving. Well, it's going to be a lot harder to stop the bowling ball rolling down the alley than it would be to stop a baseball. So a baseball, again, is a much smaller object, so a much less mass in that baseball. So the mass is, again, a measure of how hard it is to change an object's velocity. So when the pitcher throws the baseball to the catcher can very easily stop that velocity. The catcher is going to be positioned optimally so that the ball goes right to the glove and right into this glove. So that's not hard. He doesn't get injured that way. But if you threw a bowling ball at him, it'll knock him over. Chances are. So it's going to be much harder to stop that ball in motion. So when we say it's a measure of how hard it is to change the object's velocity instead of speed, so we're talking about velocity, and We want to remember again that velocity is a vector, so it has a magnitude and it has a direction. So mass is a measure of how hard it is to change either the magnitude, that's going to be our speed, or the direction. So I should put that as speed, not an m. That's not mass. We don't want to confuse that with mass. So our velocity, the magnitude, is speed, and then it has a direction. So mass is a measure of how hard it is to change the object's velocity. So mass is a measure of how hard it is to change the speed or the direction or both. So if we say an object's velocity, typically that's going to be both of them right here. But if you just change the direction of something, then you change the velocity. If you just change the speed of the object, you still change the velocity. It's one or the other or both. So if we thought of velocity in terms of an equation where you have speed and direction, if you don't change the speed but you do change the direction, you're still changing velocity, and vice versa. If you don't change the direction but you do change the speed, you still change the velocity. And of course, if you change both, then you're still changing the velocity. So that mass can also be thought of as a measure of how much matter you have, the quantity of the matter of an object. So that's what this table 5.1 is showing. It's showing how much matter the Earth has. 2 million kilograms is how much the space shuttle, how much matter the space shuttle, or how much mass the space shuttle has. A blue whale, largest animal on Earth, has a mass of 105,000 kilograms. So it's that's how much of that blue whale that we would have if we had one. One whale shark was 18,000 kilograms of mass or of matter. 70 kilograms for a human adult. And then, of course, here's the baseball. And then bacteria is in the negatives. It's very tiny, very hard to see. But that mass, again, is how much matter you have of that object. So the more matter you have, the more mass you have. An object's going to be much more difficult to start, stop, or change that velocity. Start the direction and speed, stop the direction and speed, change the velocity, changing one or the other, changing or both, changing the speed, changing the direction, or changing both. So again, the more matter you have, the more difficult it is to change that velocity. So Newton's first law of motion, it says, so we want to think of that. We want to think of before we even define that law, we've said that forces are a push or a pull. So if we're applying a force to an object, if we're pushing it or pulling it, does it stop moving once you stop pushing and pulling? The answer is yes. It would stop moving, but only if there's friction. Friction's the retarding force. There was a problem I think that we did in chapter 4 that referred to a retarding force, and that's what friction is. It's arresting the motion. It's slowing it down or stopping the motion. So in the absence of any net external force, the object's going to keep on moving at that constant speed, and it's going to do so in a straight line. Or in the absence of that net force, it'll remain at rest. So if you have a table here and a book on the table, and there's no net force. There's no net force. There's no single force either. So in the absence of any net external force, that book right there is going to stay there. It's going to stay on that table. So some kind of a force has to be exerted to get that to move. So it's going to remain at rest. That's right there. But then an object moving at constant speed in a straight line. Again, think of it in terms of throwing the baseball. You threw the baseball, and in the picture that we saw gravity pull it down. But we're saying in the absence of any external force. So gravity is a force. So in the absence of gravity, you throw that baseball, and it's just going to throw it towards the pitcher or towards the batter, and it's just going to keep on going. If he misses it in the absence of any force, that baseball is just going to keep traveling in that direction. And it's going to keep doing so in a straight line because there's no gravity to pull it downward. So in the absence of gravity or any kind of external force, the object is going to keep moving at a constant speed, and it's going to stay in a straight line. So similarly, with respect to friction, a baseball player sliding on dirt is not going to slide very far before coming to a stop. And if we wanted to compare that to an ice skater or to anyone that falls on ice, you can slide really far if you have ice skates on and you just push off, you can slide real far on the friction on the ice. If you fell on the ice, you could slide real far on the ice because ice has very little friction. Not much friction at all. It's pretty much negligible. So ice is our closest comparison to being, or closest item that gives us a friction-free environment. So in comparing the baseball player to an ice skater, the baseball player is going to slide on dirt, and that friction that's built up between the baseball player and the dirt is going to make the baseball player stop sliding. But on the other hand, though, the figure skater on ice will travel very far. Will be able to slide on the ice because there's not a lot of friction. So two different applications of friction in this case. And so if you, in the absence of friction, if you stop pushing an object, then in the absence of friction, it's not going to stop. But as long as you have friction, it'll stop moving. So the first law, our little blue Billy box down here, the first law is also known as the law of inertia. So inertia is a tendency to resist change. It just wants to maintain the status quo. So in the absence of friction, the object's going to keep moving at a constant speed in a straight line. Or if you have an object at rest, it'll remain at rest. And that first law is known as the law of inertia because it's the first law is all about resisting change and staying course. So here's that first law. It's in two parts to it. An object at rest remains at rest as long as no net force acts on it. And an object moving with constant velocity continues to move with that same velocity in both speed and direction. In speed and direction. So same velocity, same speed, and in the same direction as long as no net force acts on it. So I previously said that the net force, you have your two forces acting on it. But we saw pictures with single forces. So every time we see a net force in this Newton's law, it is going to represent this configuration where you have more than one, but it's also going to be the single force too. So it's just saying that the summation in this case is friction plus no tension plus no weight plus no contact force. So everything else is zero except friction. And so that's why we can still say that when we have a single force, it actually still means a net force could mean a single force, or it can mean multiple forces. So as long as we have no force acting on it, the object is going to either stay at rest or will stay in motion. In order to change, so again, we want to remember these two bullets here. They're really important. That's Newton's law. And then down here, in order to change the velocity of an object, whether you're changing the magnitude or the direction, you need some kind of external force to act on it. It's not going to change on its own. So that's why it has to be an external force, a force external to the object. The object is not going to have the capability of changing its direction or speed. So an object at rest won't start moving on its own. We need that external force to make it move. And then an object in motion is not going to change its speed or its direction on its own either. An external force is required to do that. So you can think of that in terms of driving. Take your foot off the gas pedal. Friction and a variety of other things will slow it down. But pretty much if you put your car on cruise control, set your car on cruise control, the car is going to continue moving in that same direction, and in that with that same speed until some external force acts on it. So the external force is your foot. You put the foot on the brake or back on the gas pedal and press a little harder to speed up, or press on the brake to slow down. So that force again is your foot that brings about that takes you off of cruise control. So again, an object at rest or an object in motion requires an external force to make it change. So the Newton's law in application here, if we look at the first concept question, so this is the concept question number 1 in your textbook. And you're driving down the road and you hit the brakes suddenly. And as a result, your body moves forward moves toward the front of the car. So explaining that phenomenon in terms of Newton's laws, Newton's first law is the one that explains that. So here you are. So here's your car seat, and here's you sitting in your car seat. And you slam on the brake right here. You slam that brake on, but now you move forward towards the front of the car. And the reason for that is that, again, the object right here, well, actually, before we start up here, your car, the car is moving in this direction, and you're sitting in it. So you're inside the car. And so you're moving at the same velocity as the car. So even though you're at rest on the seat, you're moving at the same velocity as the car. So when the brakes get slammed on, the car stops, but you don't, unless you're buckled in. If you got your seatbelt on, you're just going to jerk a little bit towards the front, but you won't go smashing into the windshield. If you don't have any restraint on, if you're not wearing your seatbelt, your whole body is gonna move toward the front of the car when the brakes get slammed, because you're gonna continue moving at that velocity, at that speed. So whatever the speed is, you're gonna move at that speed. So you're gonna move at that speed that the car is at before the brakes were slammed on. So another concept question is that when a dog gets wet, it shakes its body from head to tail and side to side to shed the water. So explaining why that works, explaining why that's a good idea, or why a dog would get rid of water that way, we would apply Newton's first law here too. So we see the dog here. So we see the dog and the tail. And the dog is going to shake back and forth in this direction. He's going to go left to right to shed the water off. And same thing, maybe moving head left to right. And what happens is that the beads are on the fur, beads of water are on the fur, but they're not restrained. Just like in the last example with the car, if you don't wear your seatbelt, you're going to move far forward a lot. And even when you do wear your seatbelt, it's going to hold you. Your natural tendency is still to move forward, but the seatbelt will stop that from happening. Well, with the dog, all the water beads on the dog's fur, they're not strapped in place or forced to stay on one strand of dog hair. Instead, they're just kind of loosely bound and laying on the dog. So the first motion of the dog when he first moves this way, all the beads are going to come that way too. But then when he goes in the opposite direction, that's going to fly all the beads of water right off the fur in that direction. So you're getting ready here, and then you go that way, and all the water then starts coming off the dog. So the object, as soon as the dog starts shaking, he puts an object, or he puts the water on his fur in motion, and then when he stops and changes direction, it's going to make those bees move off the dog faster. So the first law again is the total force from all directions. That's your net effect of the force, or the net force. When we get to 3 dimensions, the directions are going to be x, y, and z. But that we won't get the 3 dimensions until the spring. And then if that total force is 0, nothing happens. So an example is arm wrestling. You got 2 people arm wrestling here, and they're at equilibrium. Nobody's moving left. There's no movement left. There's no movement right. You're just basically holding steady at the middle. So the total force, you know you have a force. You're both pushing on each other's hands. So one hand. So you know that you have a force, but here the total force, one force is positive, the other force is negative. So when we sum them together, we wind up with the sum of those together is equal to 0. So if the total force is zero, nothing happens at all, and the object is either going to stay at rest, or if the object's moving, it's going to continue moving with that same constant velocity. So the first law is known as the law of inertia, with inertia being defined as a tendency to do nothing or to remain unchanged. So according to the first law, being at rest and moving with constant velocity are actually equivalent, and we can understand that by thinking of a person sitting on a train. So the person sitting on the train sees oneself as still sitting still, but the person observing the train as the train goes by sees the person on the train as moving with the train's velocity. So both observers have their own frame of reference, called an initial reference frame, an inertial reference frame. And that's one in which the first law is true, where if you're at rest in this inertial frame, you'll remain at rest until a net force acts on it. If you're already moving, you'll continue to move at that constant velocity until a net force acts on it. So if you're accelerating, though, if you're accelerating in either of those cases, then your frame is not an inertial frame. So an inertial frame basically keeps everything as is. And then our last point here is that if an object moves with constant velocity in one inertial frame, it is possible to find another inertial frame in which the object is at rest. And then looking at our inertial frame again here, we see depends on the position of the object and the observer. So here in the acceleration or accelerating airplane, Newton's first law is not obeyed because it's not at rest. So the plane is not at rest, and then it's also not moving with constant velocity. So it's not doing that either. So in that case here, if we put the frame of the airplane, frame around the airplane, or inertial frame right here, then the plane's not it's not inertial. It's actually making itself propel or move. And then over here with the truck moves with constant velocity relative to the person on the ground. Newton's first law is obeyed in both of those frames. So they're both inertial. He's moving with constant velocity here. This one's observing over here. And when they're moving in constant velocity, we have no acceleration. And then we have our object in the inertial frame of reference. So forces can cause motion. And here we're looking at a foot that's normal right over here, this normal foot. And then here we have the ankle is overpronated, and it's a right foot, so it's moving towards the arch right there. So we have an arch, and here the vectors here the two. We have a force right here acting perfectly on that joint, and but then underneath it this vector right here is going to point towards the injury. So it's going to be it's going to lean inward and or lean into the diagnosis or the call for surgery. So if we look at supination too, it's the same thing. Here's your arch. So now you're turning outward. You're rolling out on your ankle. And then of course in this picture everything is nice and neat, lined up against each other. So we want if we either have supination or pronation, we want to get back into this middle, into that normal range. So here's some pictures again of the foot in this case here. So we have in our last picture here we had pretty much a force going up the ankle right there. So here, when you have a low arch and you're pronating, you're going to roll inwards. Your foot's going to roll inward. But then when it's the other one, supination, it's going to roll outward. There's the ankle bone right there. So the weight is on the inside edge of the sole in that case here. So what corrects this? But before we could get to that, pronation has some bad effects all the way up the line. So obviously it's painful in the foot, but then these bones right here are creating more pain on both the knee and the ankle. But then the ankle is a force too right here, and it's out of alignment, and then we have the top part of the leg right there where the femur, I'm sorry, the pelvic area tying in over here, and what we see here too is that when those joints rotate just a little bit, it's awfully painful. So how is this treated, or what else can happen with it? So forces that we're still talking about the foot here. It gives you knee damage. It gives you a lot of shin damage. It gives you Achilles tendon. So it does a lot wrong. It has a lot. Wearing orthotics is a good thing, but not necessarily is a good thing. It'll stop all the pain from coming up. But when we look at this picture here, here's the fifth metatarsal bone. And then right in there is typically where this Morton neuroma starts. So it's not a tumor, neuroma, oma. We would often think of that as a mass or a tumor, but that's not the case here. What you get is that feeling that when your foot is squeezed, if your shoes are too tight, they're not wide enough. When you step down or start walking, you get that stabbing pain right through the metatarsal, and it feels like your foot's on fire, or just that area. It hurts pretty bad. So again, when you're rolling over onto the outside of the foot, you're putting a lot of pressure there, and you're going to get that Morton's neuroma. But then also too, if your feet or if your ankle and foot's not lined up, you can get plantar fasciitis. That's a pulling in the arch. And then you can also get an Achilles tendon pain right here. Shin splints are another possibility for not correcting your pronation. And then same thing here with knee pain, and then on up the line, here's your hip bone pain. But here's the iliotibial band. That's the muscle that runs down here. It doesn't run over the patella. I shouldn't have put it over. It runs down the side, close to the knee. So it runs down close to the knee, but not over the knee. But that iliotibial band's right there. And if you overpronate too much, or if you run on an embanked road and you're running here all the time, you're going to irritate that muscle really bad. So don't run. Make sure you're running on flat surface, and then of course you want to make sure your feet are perfectly lined up. So no pronation at all, and no pronation, no supination. So bad posture due to flat feet or poor fitting footwear. And one possible improvement is motion control shoes. So this picture actually was taken from the New Balance website, but there's a lot of shoes, a lot of sneakers out there that are motion control or provide stability. And and of course you can't, it's one size fits, or one model with a variety of different sizes. But if you roll inward or you roll outward, you can get this motion control shoe. And the way that they basically make the shoe, so here's your arch right there. It's got a roll bar right there, and then of course they're a wider footprint there too, so it gives you stability there. And so it gives you this little roll bar there that maintains some stability. And so roll bar, you would think you'd roll more, but it's actually more, it's more of a flatter piece of material here that firmly plants your foot down on the ground. And then there's also force up here and then of course the arch that's providing a force. So it's kind of meant to, and no matter what your foot is, it's going to align you straight up and down with all the different forces that are being applied in that shoe. So if shoes don't work though, if shoes don't work, you can get orthotics made. So here's a picture of your before and after right here. Here's your before and you're rolling inward. So the orthotic, these are specially made orthotics. Most of the over-the-counter ones work all right, but custom-made orthotic, for this person rolling inward, the custom-made orthotic is going to put a lot of pressure, a lot of force on your arch. So it's going to be an upward push. That arch in your orthotic is an upward push. That's going to push. It's going to take this. It's going to push it right up and straighten that leg out, or straighten out that ankle joint. And then the other way here, here's your arch. So here, the custom orthotic is going to put all the pressure here on the outer side of the orthotic now, and it's going to push all that force, or that pushing force here. So it's going to it's going to be pushed along the side of your foot. So it's going to make your ankle rotate inward. So the corrective measure, it's applying a force. So the corrective measure is that it's going to apply a force, and it's a pushing force. So it's a pushing force, again, to keep your arch from rolling over, or the outside of your foot from rolling over. So now we're moving on to Newton's second law of motion. And the second law is this equation right here, that one of two equations in this chapter. So our equations get a whole lot simpler now. We're still going to use our kinematics equations. We're still going to solve problems that are going to require the use of the kinematics equations combined with this force equation here. So Newton's second law, it says if an object is acted on by a net force, it's going to experience an acceleration equal to the net force divided by the mass. So net force divided by the mass. Why are we showing it this way? This way is actually somehow or other book publishers kind of just latched onto that convention. But the real way of writing this equation is just as the way is exactly the way it says here. You have an acceleration that's equal to the net force divided by the mass. So that's really what this equation is saying. So if you see a test question that says Newton's second law is all about acceleration, that's true. That would be true. This law is all about acceleration. It's applying a force. We're still talking about force, but the force is secondary now in the second law. In the first law, it's all about force, and it's all about applying that force to a mass. Second law is all about acceleration. When you apply that, when the object's acted on, you're applying that net force, you're going to make it accelerate. So if we look back, if we want to look at this equation, though in this form here, so the reason why publishers, I guess, kind of took it this way or write it that way is because you're applying a force to a mass, and it's causing an acceleration. So cause and effect. You're causing the acceleration by applying a force. So either way, I mean, typically this is the true way of writing, the purest way of writing the equation. But you can also think of it in this form too, because again, you're applying a force to a mass, and then you get that mass to accelerate when you do so. So both the net force and the acceleration are vectors, and we see that by our vector sign here. And then the summation, this is a summation sign, a sigma or summation sign, and it indicates that multiple forces can act on an object. Doesn't have to be multiple forces. You can have one force, but either way, the summation of one force or the summation of many. And then our direction, when you apply that force, so you're applying the force to the mass and you get it to accelerate. So the direction of the acceleration is the same as the direction of the net force acting on it. So here's your acceleration, and there's your net force. So the acceleration and net force are in the same direction. Big concept question there. So Newton's second law of motion, the direction of the object's acceleration is the same as the direction of the net force acting on it. So we're going to explore that a little more here. So if you pull an object toward you, it's accelerating towards you. If you push the object upward, it's going to accelerate upward. If you push the object downward, here you can think of pushing downward, you're bouncing a basketball. Think of bouncing a basketball here. So you're pushing downward, the ball accelerates down. And then when the ball hits the ground, it's going to change direction and it's going to come back up, and then you're going to push it back down. So you push it down here and the floor pushes it back up. So again, it's a push-push right there, not a push-pull. So, and then lastly here, if you push an object to the left, it accelerates to the left. You push it to the right, it accelerates to the right. So if you're pushing to the left, and we define left as negative, the acceleration is becoming more negative. It's getting higher in magnitude. The number the magnitude, if we took magnitude of that, we just have our A. So it's going to become more negative if we're going in that direction. So the second law is actually consistent with the first. A lot of people think they're not, but the second law actually is. So if an object has a net force of 0, then the acceleration is 0. So the first law is if no net. The first law is if no net force is applied, then the object's going to continue on a straight line with a constant velocity. So if we look at this here, and this is 0. Mass will never be 0. We have an object we're exerting a force on, so the mass will never be 0. So we have an object of mass m, and we're not applying a force to it. So if we're not applying a force to it, then it's not accelerating. It's going to be moving along with this constant velocity. So if the net force is 0, the acceleration is 0. If the acceleration is 0, there's no force acting on it, and the velocity is going to be constant. We're going to see that motion in a straight line. Gravity is not even acting on it in that case here when it's going in a straight line. So Newton's first law is that an object moves and continues to move at constant velocity until a net force acts on it. So when it's at constant velocity, that means constant velocity, that means our vector A is 0. Yeah, so we're not accelerating. So think of that as cruise control again. So cruise control, you're set on set speed, and you're going to continue moving in that set speed until you apply a force to change the direction or change the speed. So without that net force, you're going to continue moving at the set speed, or moving with a constant velocity. So here's our first application of the problem here. So you're pushing a shopping cart, which means that you're exerting a force, or you're applying a force to the cart. So the magnitude, which is the strength of the force, it's given to us as 13.4 newtons. And the question is, how far does the cart move after 2.5 seconds? So we have a force and we have a time. And then we can assume that we start it from rest, and we want to know how far the object went. So we're not told what. So x naught, we'll assume it's 0, and then x final is we don't know, and we're not really given enough parameters to say. We just know 2.5, so we want to find that. So we want to find out what this is. And then we know the force is 15.4. Oh no, I'm sorry. That's not the force. So the mass is 15.4 kilograms, and the force is 13.4 newtons, and then time is 2.5 seconds. So we wrote down all the things we know, and we want to find what we don't know. So we can actually pick our kinematics equation now, And so we're going to go back to chapter 2 because we're pushing a shopping cart. So here's our shopping cart. And you're walking down and you're pushing that shopping cart. So you're pushing it, we're going to assume it's in the positive x direction. And we're going to assume you started at 0 and you're going to move in the positive x direction. So that's one-dimensional kinematics. So we can go to chapter 2 and look at the equations there. And the best one suited is equation 211. And that's the one that has our final position equal to our initial position plus that initial velocity times time plus our half at squared. So we said that x naught is 0. But even without that, we won't drop it out of the equation. We're going to rearrange the equation to be x minus x naught to give us a true delta. And then it's going to be equal not to v naught t, because if we assume that we move it, that the shopping cart, well, no, we're not assuming, it actually tells us we're starting at rest. So starting at rest means that v naught is 0. So that drops out of the equation and we get our half at squared. So we get our delta x right here equals half at squared. And but we don't know what a is. We need to calculate. We're not given that value. So I'm going to erase our little shopping cart here because we need some space to solve for a. So our solving for a, we're going to take advantage of this equation here. F equals ma. Actually, let me move that over. So we're going to take advantage of that. We're going to say F equals ma. And then, and we want to solve for the acceleration. So that equals F over m. And we have a force of 13.4 newtons divided by 15.4 kilograms. And that gives us an acceleration equal to 0.9 meters per second squared. So now we can come back down to this equation here, and we can say that delta x equals half times our 0.9 times our t squared, our 2.5 seconds, and we're going to square that. So that ends up, so when we go ahead and plug those numbers in, that means delta x is 28 meters. So what we're saying is that the cart moved 28 meters in 2.5 seconds once you started pushing it from rest. So there's our answer for this one. And then now we're going to push that cart up a hill. And so we're going to push the cart up the hill, and it's a hill that's a 13 degree hill. So we want to think that our triangle is this one right here, but actually that's not. The force that you're applying to it is completely in the straight line right there. It's just the x-axis right there. So there's no y component. She's not boring down on the cart. She's just pushing right there. She's exerting a horizontal push to it. So the y component is 0. So that's one dimension. But then you got to go up this hill here, and so we need to find the horizontal force, which is F sub x. So that's what we need in it. That's what we want to find. And so we also can take into account. We see our acceleration there, going in the same direction as the applied force, and then so we want to also take into account the weight of the shopping cart. So there's our weight acting downward, and so we got to consider that because we want to know. We want to find the magnitude and the horizontal force needed to give the cart a particular acceleration, to make the cart accelerate by 1.4 meters per second squared. So we got to account for the heaviness of the cart and all the groceries in it. So we got to take that into account. So our F of x equation becomes the summation of the applied force plus the weight. And so now we don't really need our kinematics equations, But we do need the sine and cosine functions here. So so we're going to take our applied force times our cosine of theta. So that's our f of x right here. This is our f of x cosine theta, and then and that's our f of x applied, and then we're going to add to that the applied force times the sine of theta. So this is in the y direction, but it's in the y direction, but we know that that'll drop out. And then our value for weight is mg, and so it's going to be mg sine of theta. Let me erase all this here. So we have that as our mg sine of theta. And we have to have that equal to. So all of this right here is our f, and it happens to be the x components of it. But remember that f equals ma. So we have our f here, and we're going to set that equal to ma. So so we can shorten this a little bit here, where we have our f cosine theta plus our mg sine of theta equals ma. And then now we want to solve for the force. So we're going to bring this cosine over to the other side of the sine part over to the other side of the equation. So we get f cosine theta equals ma minus mg sine of theta. So now we can divide through by cosine, and we get f over here equal to, and we'll pull the m out, a minus g sine of theta divided by cosine of theta. So now we can just plug everything in, and we get a force equal to 28 newtons. And then another force problem right here, where we have a 0.53 kilogram billiard ball. So we're going to look for the average force during the time interval that the ball is actually in motion. So we're going to start with Newton's first law. So we know F equals ma. So we got Newton's first law, and then and we know that the acceleration is a change in velocity. We know that acceleration is a change in velocity over time. So and then we also know that delta v means v final minus v initial, and then this is t final minus t initial. And so now we can go ahead and take this part right here and put it back in our F equals ma equation. So we want to substitute that in here. So our force equals our mass times our final velocity minus initial velocity. And then I'm just going to put our 4 milliseconds down here. And so that's 10 to the negative third seconds. So we want to make sure we keep everything in SI units. And so we can now take this V final, or we can go ahead and then put in our we can go ahead and substitute this part for actually I'm not going to erase anything. We're just going to go down here, and our mass is 0.53 kilograms, and then our final velocity minus our initial, we ended up with or this whole part right there, this calculates right here. The delta, or the A value, A calculates to 3,000 meters per second squared. So we can go ahead and put that right in here, 3,000 meters per second squared, and we get that the force equals 1,590 newtons, or rounding 1.6 kilonewtons for that part. So we found the average force is is 1.6 kilonewtons, and we did that by utilizing our understanding of acceleration being change in velocity over time, and then inserting that into the F equals ma equation. So a little bit more practice. You're driving home from school, and you spot a ball. Spot a ball running out in the street. So you brake for 1.2 seconds to slow down, and we have our time and we have our mass and a change in velocity. So we want to find the force. So we're going to do the same thing we did the last time. We got our force vector equals ma, and then we don't have anything for a, but we have our velocity right there. So we're going to rearrange or rewrite that equals to m times our delta v over delta t. So we'll just put a equals delta v over delta t. So our delta v is going to be our final is 9.5. So our final is 9.5 minus our initial divided by that time value, 1.20 seconds, and this is in the x direction. So our force equals when we calculate it, when we actually go ahead and calculate this through. Remember to put the mass value, the 950 kilograms, right up here. So that force comes out to be 5,100 newtons, but it does so in it's actually a negative 5,100, and so you're slowing down. That would make sense. The force is one where you're braking, so you're braking as a force, and you're going to slow down. So that negative sign indicates you're slowing down. So to find the distance now, we're going to get back to our kinematics equations, and we're going to use equation 210. And equation 210 is our x minus x naught equal to half times the average of the velocities times time. And then when you plug everything in, you get x equals 15.3 meters. So Newton's second law of motion, when you have two equal weights, so this is really talking about proportionality here, and that's a lot of what appears on the MCAT. So you'll get MCAT questions about a particular volume or an area or a circumference, and it'll ask something like, if you hold one value, like what happens to one value when you double the other? So that line of thought or that type of reasoning, that's what we're going to show here too. So we're going to see our F equals ma. So if you have two equal weights in series, we have one weight here, and then we have two of them in series. They exert twice the force. So when we doubled our mass, we doubled our force right here. So we have our new force is double, and it gives us our F2 if we wanted to. So when we double the mass here, we double the force, and that's what this picture is showing here. And then similarly, if we cut F in half, then we're going to cut the mass in half as well. So this is considered when we have them together or doubled up right there. That's what is called series. Parallel would be if they hung this way. So when they're in series, they're going to actually it's going to actually increase. It's going to cause twice the force when you double that weight. And then the other part of this is the acceleration. So we still have our F equals ma. But now we're holding this constant here, and we're going to change this part. We're going to double we're going to see what happens to the acceleration. So if you double the force, then you got to double the acceleration as well. And we can see that visually here. We have our mass, and that remains unchanged, but we double the force, and that means the acceleration is also doubled. So Newton's second law, acceleration is inversely proportional to mass. And that goes back to our equation here, where we have our force divided by our mass. So the acceleration equals force divided by mass. So acceleration and mass are inversely proportional and directly proportional to F. So Newton's second law, an object may have several forces acting on it, and the acceleration is due to that net force. So again, we're going to do that summation there. And three different things to measure weight. We have our Newton, our dyne, and our pound. And then Newton's second law of motion, we always want to draw that free body diagram to show every external force acting on the object, and then define or draw the coordinate systems in conjunction with the free body diagram. And then you can sketch the forces represented by the vectors on your coordinate system. So it's hard to visualize what it looks like. So if you're pulling, you're going to have a pull. You have a pull here, friction this way. So we're still praying for you. But again, we have this force that's going in this direction here, and then our friction force. So we want to sketch all the forces that we've got, isolate them, and then you can make it a point. You can make it a point particle here, which are all the force vectors summarizing down like we made the house a point. So when we isolate the object of interest right here or right here, whatever it is, either way, we're going to make sure that the vectors either point towards the object or away from the object. And then we're going to resolve the force into its components and then apply Newton's law to each coordinate system or each coordinate direction. So here's what that looks like, our free body diagram. So we're looking at the forces on this pillow here, and we see the chair is providing a support. It's providing the normal, and then the weight is acting down, and then here's the weight of the pillow or the force of the pillow against the armrest. So n sub x is 0. There's no value of n over here, but n sub y is the full amount of the normal force. So again, recall the relationship here. And then same thing with weight. Weight's a force, and it's only moving in the negative y direction. So w in the x direction 0. And then we have our force that we, in the familiar form that we saw it in chapter 3. So choose an upward to be positive. We have our n is positive and w is down. So when we want to sum all of those forces, all of our forces are in the y direction. So we do this here. We have our applied force or the force of the pillow, the weight, and the normal force. And then because the acceleration is 0, that means the pillow's at rest. So then we can use the y component of Newton's second law. And when we do that, we end up our summation, this is our F equals ma. So our F is our force minus our weight. And the normal, it shows that the normal, the normal, if we did this right here, we get this equal to ma, so that's 0. And we get the weight equal to the, or remove the w over here to this side of the equation. So we end up with n equals w. And so it's only true, so ny and, or the normal y in the y direction and the weight in the y direction, or they equal each other, but that's only true when n and w actually oppose each other. So if we look back at the previous slide, they oppose each other because the normal is up and the weight's down. So we can take advantage of this relationship here, that only holds true when they actually oppose each other. as shown in the previous slide. So we want to remember that N and W are vectors, so they can be oriented in 2D, and that means that they won't cancel each other. So now Newton's second law of motion, here we start again with our force that's supporting it, and then the weight pulling down on it. So when we take our F equals ma, the acceleration 0. So then we end up with F equals W, and or we could say N equals W right here. And so here W shows the downward force of gravity equal to the upward force exerted on the object by whatever the object's resting on. So if it's resting in your hand, it's a normal. So this force is going to actually be a normal force. So Newton's third law is that states for every action there's an equal and opposite reaction. So again, they come in push or pull pairs, and the forces always come in pairs with each force acting on different objects, so they don't cancel each other out. They don't cancel so a pair. So N and W would cancel out because they're both acting on the same thing. But because these are acting on different objects, their push or pull force combinations won't actually. They're going to come in pairs, but each force is going to act on a different object. So if object 1 is exerting a force on object 2, then object 2 is exerting a force back on object 1. So that's the gist of the action-reaction pair. So we'll take a look at that right here. So the force is friction. So we have our friction right here, and it's the car on the ground friction is going to pull it this way, and so the wheel's going to move that way. And then, so we have two objects, the ground and the car, or the ground and the wheel. And then same thing right here. You have this guy pushing on this refrigerator, and it's hard to move, so the refrigerator's actually pushing back on him. So the guy, if we draw that system, he's acting on the refrigerator, and then the refrigerator's acting on him. So if they were both acting on a chair or a box, then we can say that the forces would cancel each other out. But because the refrigerator is not acting on the refrigerator, it's acting on the man, and the man is not acting on himself, he's acting on the refrigerator. So different scenarios where we see that equal and opposite or action-reaction pair, where they're not equal and opposite, they don't cancel each other out. And another one to keep in mind is the Earth pulling everything to the center, so it's pulling down on the space shuttle, but similarly the shuttle's pulling upward on it. So action and reaction pairs do not cancel out because they're acting on different objects. So person pushing the refrigerator, the person is exerting a force on the fridge, and that's the action force. The reaction force is the force from the refrigerator pushing back on the person. So we want to isolate the isolation step of the free body diagram. That'll help us isolate the person from the refrigerator, and then to calculate the force that the person's exhibiting or exerting on the refrigerator, and then we can calculate the force of the fridge the force that the fridge is exerting on the person. So the third law is although the forces are the same, the accelerations will not be unless the objects have the same mass. So when the objects have different masses, the accelerations are going to be different. And again, remember that F equals ma. So we have same force here. We have the same force but different masses. So you have an F equals ma here and an F equals ma here. So our contact, but what we really want to look at with this picture is this contact force. So contact forces are when objects are touching one another, and the force exerted from one box onto the other is different depending on which one you push. So if you're pushing here, you're going to have a contact force here, and that's going to try and move this box. But if you're pushing here, you got this contact force, and it might actually just topple the box over, or it might just make everything move in the same direction. So the force exerted by one box on the other is different depending on which way you push. And when you push on a small box, the contact force is actually going to be larger than if we push from the other side. So we're going to look at an example of a problem that we want to solve here. So we have our three we have three boxes here. So this one's 1.3 kilograms. This one's 3.2, and then this one is 4.5, and then the force is the applied force is 7.50 meters or newtons. So we want to find the magnitude of the contact force. So the force is exerted on the first box, which then exerts a force on the second box. And then the second box exerts a force on the third. So this could be 1, 2, and 3. So since there's only one force and there's three masses, the acceleration must be a constant then, and that all three boxes will experience. So what we want to start out with is our equation. We know F equals ma, and we can arrange that to A equals F over m. So to solve that, our acceleration equals our first mass plus our second mass plus our third mass, and they're all dividing into the force here. So we can go ahead and plug the numbers in, and the acceleration that we get is 0.798 meters per second squared. And then we want to find the force, the contact force on between boxes 1 and 2. So I'm going to rate our acceleration 0.798. I don't want to forget that. So our force is on the force is is the contact force between boxes 1 and 2. So when we look at the box, our summation of all of our forces is going to be is going to look like the applied force minus the contact force between them, and that's going to equal m1 times a. So we just want this contact force. So we're going to do F, and we're going to bring this ma over here. F equals m or ma. Actually, let me erase that here. So we have our F minus ma equals F contact force between 1 and 2. So so that gives us a contact force of that gives us the contact force between C1 and 2 as 6.46 newtons. And then for the next one, for the third box is what we want to find. So that's the force, the contact force between boxes 2 and 3, and that's going to equal our ma. So we wind up with just substituting m in 4.9 kilograms times the 0.79, and that's in meters per second squared. So when we calculate that, our answer is a force of 3. Our force gives us 391 or 3.91 newtons. So another way to solve this is to think of the contact force between 1 and 2 as accelerating boxes 2 and 3, and you can do you can actually take our summation of our forces, and then equal to m1 plus m3 times a. So that's an alternative way of solving it. and you get the same answer if you wanted to go that route. So the vector nature of forces, this is a common picture right here where we have our 52 degrees and then there's our triangle, and sometimes they don't always give us a nice neat little square like that, but this is pretty rare. We won't see much of that. So here's our cover picture, and we have a couple of teens pulling this cords, and they're pulling with a force of 55 newtons at an angle of 35 degrees. So that's 35 degrees. And then again, we have our two triangles. So friction we haven't really learned yet. So here's the problem with the retarding force, not on the last exam. So that's what this one is. This is the force of friction right here. And it's a retarding force because it slows down the sled on the snow. So you have to work against that. So by pulling the object in the direction opposite the direction of motion, that's what the friction force does. So friction is it's a force, and it's more specifically friction's a force, but more specifically, it's a retarding force or it's a slowing force. It slows down the object by pulling the object in the direction opposite that of motion. So here's the direction of motion, and here's your F sub x. It's in the opposite direction. So our vector analysis for this problem is really important, and I'm going to draw the pictures here. So here's a triangle right up here. So we get that triangle, and then here's another triangle down here. So we get that triangle down here, and then our A is just right through the center, doesn't get changed. And then we have our F sub x here and our F sub y, F sub y, and then F sub x right here, because here's our angles right there. So when we see this though, when we see this acceleration I drew the acceleration backwards. So we see the acceleration in the same direction as the force, in the x component in particular. So for the acceleration, it's a one dimension, so it's only in the x direction, which means that vector A equals the x component. But now we can look at the force triangles, these two triangles right here. And we know from our concepts that if the force and the acceleration are in the same direction, that means then Fy is extremely small and actually should be 0 compared to F sub x. So looking at F sub y on each triangle, we see that they're equal in strength. They're the same size, so equal in magnitude, but opposite in direction. So when we sum the forces in the y direction, they're equal and opposite. So they're going to sum up to 0, and what we end up with there is F sub y equals F sub y1 minus F sub y2, of course that's just setting up the summation, or MA, and we end up with F sub 1 equals F sub 2, and when we group them together, the 1 is negative. So that means we don't have to take into account the y part, and what we can do now is look at our trigonometry and then go on to the x part, the x components here. So when we do that, we see that F sub x is the same magnitude on both sides and in the same direction. So we'll write down our force, the summation of our force in the x direction, and that's going to equal. Let me write that. Let me make that a little smaller here. So we end up with we start with our F sub x equals our F cosine of theta plus our F cosine theta for the other for the other triangle. So cosine theta right here and cosine theta right here as well. So and then we have to. So this is our cosine theta. And then we also have to keep this friction in there. So we're going to subtract our friction force. So now that we have that all set up, we can go ahead and we can rearrange. We still have to actually set that equal to MA. So these are our forces, and so our force equals MA. So we don't want to forget that. We want to group in all of our forces together, and we got to set it equal to MA. So so now the mass and the MA side of the equation, that means the mass of the sled plus the mass of the child. So we can rearrange the equations and rearrange this equation, and we can say the summation of our force X is going to actually equal 2 equals 2f cosine theta. So it's these two that get added together. Let me write that a little neater. Equals 2 cosine theta minus f. So and that equals our MA. So that equals our mass of the child plus the mass of the sled. So again, this is minus F equals MA. So so the MA here, that's the mass of the child plus mass of the sled times the acceleration. And the acceleration is what we want to solve for. So we're going to take this part here and we're just going to divide mass of the child plus mass of the sled, and that's going to be equal to our acceleration. So now you can plug the numbers in and we get the acceleration equals 1.5 meters per second squared. It's again 1.5 meters per second squared. So weight is our second equation here, and it's always going to be defined as gravity acting on the mass. So our weight is going to be mass times gravity. So it's the weight of an object on the Earth's surface, and it's the gravitational force exerted on it by the Earth. So apparent weight is your perception of weight based on contact forces between you and your body. We're not really going to get into apparent weight, but you can take a look at it. You can take a look or read it. But our normal force is very important. So our normal force, again, is the force exerted by the surface on an object. So it's a support again. So here we have a table supporting the bowl. So the items, the weight goes down, and then our normal is up. Same thing here. The normal is the perpendicular to the surface, so it's pointing up, but W points down. And then same thing here with this can. Normal is up and weight is down. So normal is always perpendicular to the surface on which it's acting. And then, and it's a vector, so you can break it down into vector components. But in this case here, the vector equals the n sub x, so you don't have to really do a lot of calculations there. So the normal force can be equal to, greater than, or less than the weight. They don't always. It's not always this nice and neat n and minus w where they cancel out. It's not always like that. So you can have this block of chalk, and they're pushing on it. So we would have to do the math in each scenario to figure out if it's greater than or less than or equal to. So the normal force, again, is always perpendicular to the surface. So that's what this picture's saying. We have our surface right here, and then our normal is actually perpendicular to that. So again, the normal force is perpendicular to the surface on which the object is resting. So I think this is our last problem here. So we have a child sitting in a high chair, and we want to draw a free body diagram of the child and find the normal force exerted by the chair on the child. So for A, we have a high chair, and we have a child sitting in the high chair. So the free body diagram has to include the forces. So the chair is supporting the child. So we have the normal force, and then the child's weight is acting down. So there's our free body diagram for the first one. And then for the second one here, so we have a child sitting here on this chair, and so now it's in relation. This is the normal force exerted by the child on the chair. I'm sorry. B is draw the free body diagram for the chair, and then find the normal force. So the chair is being supported by the floor. So here's our normal force right here, and then the chair is actually supporting the child, is supporting the child. But we don't need that though, because the normal force supporting the child, we don't need, because we want to find the normal force exerted by right down here. So the other forces are, so those forces are, again, there's three of them. The three forces are that are on the chair are this normal force that's exerted on the chair by the floor, and then and it's acting upward, and then the weight of the chair, the weight of the child, and the weight of the chair, both are acting downwards. So both here's the weight of the chair and weight of the child. So here's our three forces, and then so we can come over here and for A. So for A, we want the summation of our forces in the y direction, and we're going to set it equal to F equals ma again. So our F's are the normal force for the chair minus the weight of the child, and let me erase all this. I can start over and write that a little neater, smaller actually. So we have this normal force right there. So for A, we're going to sum up our forces in the y direction. So again, that's in the y direction. That's the normal of the chair minus the weight of the child. And then we set that equal to ma, and the acceleration is 0. So acceleration is 0. So we have our F equals ma right over there, and we can see now that our forces are n and the weight are the dominant forces acting now. So that's actually or we can actually put numbers in now. So the n value of the chair is, so this is the n value of the chair. So the normal for the chair equals mg, and then that means m is 9.3, and 9.3 for the child, and then that's going to be times our 9.81 meters per second squared, and that gives us the normal for the child equals 91 newtons. And then we do the same thing for F sub y. f sub y equals the normal for the floor of our f sub y equals the normal for the floor minus the mass of the child minus the mass of the adult, and that equals ma, which equals 0. So f sub y, we can rearrange that. So this is the equation we want to look at right here now. So f sub y is it becomes our f sub y becomes the n of the floor minus the mass of the child minus the mass of the chair, divided now by f sub x, and that equals 0. So now we can just plug in the masses. Actually, I'm going to erase this. That's awful hard to read, so I'm going to write that a little neater for B. So for B, we have our summation of Fy, and so our F's are the normal for the floor supporting the chair, the mass of the child, and the mass of the chair, and that's all going to be divided by the F sub x, and then or no, I'm sorry, that is our F, so we're not dividing by that. And it's not X. All of this right there is F sub Y, and then we set it equal to F equals ma. So and then the acceleration, this a value is 0 because the child is sitting in the chair, so that helps a lot. So we can make that equal 0, and so now so when we make that equal to 0, we're going to take these two values right here and move them to this side of the equation because we want to solve for n sub f. So the mass of the chair and then the mass of the child, and we see we had that mg there. So let me fix this here. Yes, so we had our just like we had the mg up here, we have the mass of the chair and child times gravity. So when we solve for n sub f, we're going to take the mass of the chair minus the mass of the child times g to the other side of the equation, and then we can substitute now, and we get 9.3 for the one child plus 3.7 for the other child times 9.81 meters per second squared, and we get the normal for the floor equal to 130 newtons. So if you have any questions, I think we went through that pretty quick. Maybe are hard to write with some of these problems here, but please do reach out and ask any questions you have. So take care.